Welcome to 5.1 example 1. This is where we start to look at the graphs themselves, and we'll do some vertical and horizontal stretching within 5.1 as well. But right off the bat, if we're going to graph y equals sine theta, it is really important, and I'm going to reveal the graph in a minute here, but I want to talk about what we're doing here is we are looking at the unit circle and then ultimately looking at several points along that unit circle. And I'm just going to write a few down, and we're going to work in degree mode to make this a little bit more clear. But basically, the concept behind this graph is that whatever angle that I've put in is the x, and then the y coordinate of that angle on the unit circle, which is a bit of a mouthful. So make sure you're understanding what I'm saying, that if I draw the unit circle, whatever point that angle's terminal arm intersects with the unit circle, the y coordinate is the value of the sine of that angle. Now, looking at that a little more functionally, because I wrote p 0 degrees is equal to 1 comma 0, this lets me know that the sine of 0 degrees is equal to 0. Whereas the point at 30 is root 3 over 2 comma 1 half. So the sine of 30 degrees is equal to 1 half. Now it's important that both of those are points. Right? Keep in mind that on this graph, y is equal to sine theta. So this would be the point, and I'm going to write 0 degrees comma 0 because the input theta is in degrees and the output is a number, so it doesn't have a unit attached to it. It's the ratio of the opposite hypotenuse side. So the sine of 30 degrees equals 1 half lets me know that 30 degrees comma 1 half is on that graph. And I'm just going to write these other three, and then we'll extend our knowledge of the unit circle to the points beyond. So the point at 45 degrees is root 2 over 2 comma root 2 over 2, which means that on my graph, I will have 45 degrees comma root 2 over 2. And then the point at 60 is 1 half comma root 3 over 2, and the point at 90 is 0 comma 1. Now both of those, again, the input of y equals sine theta is the angle, so this would yield 60 degrees comma root 3 over 2, and then we would have 90 degrees comma 1. Now, for all the points beyond, you really just have to think about the unit circle itself. So I'm going to reveal that graph, and we'll certainly talk about this in detail as we go on. Really, really important. And I like chopping this graph up a little bit. I just want to leave kind of a blank version of it or an untouched version of it so that you can kind of examine it and copy it down. But what I like doing, at least at some point, is talking about that on this graph, we can actually represent our quadrants. So from 0 to 90 degrees is quadrant 1. From 90 degrees to 180 degrees is quadrant 2. From 180 to 270 is quadrant 3. And then finally, this last section here is quadrant 4. Now, this is just a graph of one positive rotation. This graph would continue forever in both of those directions. And this pattern would be reproduced again and again and again. Now, according to CAST, I'll write it down here, is when we look at quadrant 1, the sign should be positive. In quadrant 2, sign should be positive. In quadrant 3, sign should be negative. And in quadrant 4, sign should be negative. And our graph shows that to be true. Now, the concept behind that we've also pushed a fair amount is that in quadrant 1, the x is positive and the y is positive. So the cos of all angles is positive and the sine of all angles is positive. In quadrant 2, my x's are negatives, my y's are positive. So cos is negative and sine is positive. And then if we fill out the rest of these, we can see that anywhere the y coordinate would be negative, the sine of that angle is negative as well. Now, the next part of this question wanted us to describe what we saw in that curve. And I have just kind of a bit of a short list of things that we should notice as the graph is periodic. And I'm just going to put in brackets here that basically just means it repeats its pattern. And I won't write it, but really it repeats its pattern periodically. That's every period. And we'll talk about what the period of that function is. It is continuous. Now, this is not something we deal with yet, but this is basically just something that we talk about a lot in calculus. When a graph is continuous, it means it's differentiable, which means we can find the slope and do a kind of, we get access to a maybe calculus toolbox. We want to use that language. Okay, domain. A little bit tricky to see from that graph, but theta would just be an element of the real. You can take the sine, or cos for that matter, of any angle. So when we start to talk about tan, that domain can get a little bit trickier. The range, and we definitely referred to this in one of the chapter 4 videos, is that the sine of an angle is never greater than 1, and it's never less than negative 1. So my range is that y must exist between negative 1 and positive 1, but it can be any real number within that range. Okay, maximum, the absolute highest point on this graph is when y is equal to 1. The minimum is the lowest point on that graph. It's when y is equal to -1. Really important that these are linked to the range. The range should be the minimum point and the maximum point, if there is one, right? We could go to infinity on some graphs. Now, another concept that we're going to talk about quite a bit is something called amplitude. Amplitude is really defined as the distance from the equilibrium line to the max or the min without worrying about direction, right? So it's one away in this case. I am going to give you a formula right now. We're going to use this quite a bit in chapter 4, but the formula for amplitude is it's the maximum value minus the minimum value divided by 2. I'll do that for this question then. That's +1 minus -1 divided by 2, which is 2 over 2. So my amplitude is just 1. All right, just a couple things left to talk about. I know there's a fair amount going on here. The period of this function is how long it takes to repeat, and we have already talked about this. We've talked about how coterminal angles are ultimately, they have the same terminal arm. That's what period is all about, and coterminal would be 360 degrees, or the coterminal addition that we would do. All right, y-intercept, nice and easy. I always like writing this. Remember that for every y-intercept, x is equal to 0, and on this curve, that occurs at 0. The sign of 0 is 0. X-intercept is a little bit trickier. To do that x-intercept, I got to rewrite that. It looks too weird for me. We could rather make a long list of x-intercepts, and I think that's worth doing. I'm going to start at -180 degrees. 0 degrees would be in there, 180 degrees would be there, 360 degrees would be there. And then really importantly, remember, we can exploit coterminal angles. So I am going to add 360 to 180, make sure I do this right, and I get 540 degrees. Next would be 720 degrees. And importantly, that pattern is going to continue due to the period of our function, right? It repeats every 360 degrees. That means that we have infinite x-intercepts, which means we can't actually list them. Now, this is a kind of a cop-out, is saying that the x-intercepts are, and I shouldn't say x-intercepts, should I? That is definitely an oversight. These are theta-intercepts because that x-axis is in an angle. I could say that theta is equal to and write that list out. That's very cumbersome. There's a much better way of writing this. And I think it is important that every single number on this list is a multiple of 180, including 0, as long as we consider that 0 is also an integer. So I would write that as theta, the value of the angle that gives me a sine of that angle being 0, is 180 degrees n, where n is any integer. I'm just going to write it below that 0 is an integer. So that still does cover our 0-degree angle. Okay, that's really all they wanted in that first question. And then the remaining part of 5.1 is going to be applying those transformations that we learned about and used in chapter 1 and 2 and 3. Chapter 5 brings that home, except we're going to use trig functions as opposed to, polynomials or radicals.